Okay, in 7.6 we're going to revisit modeling with data. We already know how to deal with modeling with linear regression. If we have a scatter plot of data that looks fairly linear, we generally find the regression line, okay, which we do with our calculator, where we use stat edit, put the data in there, and we do stat calculate and do linear regression. It gives us a line of best fit that models that data, and then of course with the line that we have, we can use that to make predictions. Okay. Now, what we're going to do in this section, though, is we're going to expand that to some other types of modeling with different functions that we've learned about. Okay, and so we're going to start with exponential functions. Okay, an exponential function, remember, is of the form y equals b to the x. We have some base to the x power. Recognize that that's an exponential function. Okay, and what we're going to look at first is before we use them for modeling, I want to look at some information about exponential functions. So we're going to start with this function 2 to the x. If we want to, first of all, if we want to graph that type of function, we're just going to take our numbers. We usually use -3 to 3, gives us 7 points that we can plug in here. Remember, one of our rules for exponents, if we have a negative exponent, we write that as 1 over 2 to the 3, okay, which turns out to be 1/8, and then 1/4, 1/2, and so on. And of course, if you have your graphing calculator, you can do the same thing with your graphing calculator by putting that into your y equals. We put 2 to the x, and then we put our table set on auto, starting at -3, and hit table. And we can see that we have the decimal version of those same numbers here. And with that said, we can look at the points. We can make our XY chart with that. We can also hit graph, and we can see that the graph is a curve that goes up as it goes to the right. Okay, we call that an exponential growth curve. I'm going to go ahead and turn my stat plot off just so we don't see those points that are plotted there. We'll use those in a minute again. But ultimately our graph then would look something like that. And we call that an exponential growth curve. Okay. So there's the slide of it. Notice it goes through 0, 1 because 2 to the 0 is 1. Any base is going to have that feature no matter what the base is. To the 0 power is always going to give us 1. So if it's 2 to the x or 5 to the x or 10 to the x or whatever, okay, they should all have the same general shape. They should all go through 0, 1. The bigger the base, the faster they're going to grow on the right side of the y-axis. Okay. So what we're going to do here is we're going to compare a couple of models here. They give us some data about world population here. One is a bar graph, the other is a scatter plot. When we look at the scatter plot, this looks fairly linear. Okay. And so ultimately, if we enter that data into our calculator and we do linear regression, it gives us this slope and y-intercept. Okay, with exponential regression, it gives us the a and b of this form, so it's going to be a times b to the x. Okay, so I want to talk about that exponential regression just to make sure we know where it's at with our calculator. If we hit our stat button, calculate, and your linear regression is right here at number 4 for most calculators. And if you go down to the exponential regression, that's my number 10. Okay, and all we want to do here to do exponential regression is hit enter, enter, and then it'll work. So let's go ahead and put that data into the population. Just to review that part. Okay, we're going to do years since 1950. So when we put our stat edit, we're going to use year 0, then year 10, and then year 20. We're going to years after 1950 because that's the given year that we had. So 30, 40, 50, and then we have 2008, which would be 58 years beyond. And then if we put our population data in there, we got 2.6, 3, 3.7, 4.5, 5.3, 6.1, 6.8, and once again, to get the linear model for that, we're going to go stat, calculate, linear regression, and we can see that same y-intercept and slope that we saw on the previous slide, which we'll go back to in a minute. And we can also do stat, calculate, and we'll do exponential regression, and that will give us the a and b that we mentioned in the previous slide also. Okay. So, with that said, the part A of the question here is going to be similar to the questions we're going to have to answer is express each model in function notation with numbers rounded to 3 decimal places. Okay? And then how well do the functions model this population in 2008? Okay? So what we're going to do is then write the two, oh, there's a part C here by the way. By one projection, the world population is supposed to be 2026. And it says which function serves as a better model to predict. Okay? And ultimately, the function notation they ask us for in part A is going to be, we have 3 decimal places. This is the slope and the y-intercept that we found. And with the exponential, this is going to be our A and our B. Okay? And then ultimately, we want to use those to make predictions for the first part. We'll go back to the question. They ask us how well did the functions model the population in 2008. Okay. And I am going to make in my y equals, I'm going to go ahead and put those two equations in. So it was negative 0.074x plus 2.287. So that's my linear model. 2.566, 1.017 to the x. Alright, so if we put those in there as such, and we want to know how good a predictor they are for 2008, okay, what we're going to do then is put in, remember this is since 1950, so I'm going to do my, I'm going to put in 58, because that's 58 years beyond the initial year. So I'm going to do that with my calculator though. I'm going to put my table set on ask, and I'm going to hit my table, and I'm going to type in 58, and that's going to give me the two predictions here. And remember the actual number was 6.8. for 2008. So which model did better? Did the linear model or the exponential model? And in this case, the exponential model is clearly better. It gave us 6.8. This one gave us 6.5. 6.6 if we round to the nearest tenth. 6.8 if nearest tenth. So the exponential model is better. Because remember, I put my linear in y1 and my exponential in y2. And then they also asked us to do the year 2026 for part 2. So part C, that is. So then after 50 years, that would be a 76 years after. Okay. And so this one predicts 7.9 million, this one predicts 9.2 million, and they said the actual is 8 billion. And so which one's better in this case? Well, in this case, the linear would be better. The exponential would be way too high. Okay, this one's very close to 8 billion. This one's quite a bit higher than 8 billion. So in this case, the linear would do a better job than the exponential for that particular question. Okay. Right. Now, I do want to talk with exponential functions. There is a special base. We said 2 to the x, 10 to the x, 5 to the x, and so on. Okay, there is a special function that we call the natural exponential function, and that's the base e to the x. Okay, you have e on your calculator right over here on the left. It's above the ln button. So if I go second e and I go to the 1, it's going to give me the decimal for e, which is 2.718281828. Does not repeat or terminate. It's an irrational number, very similar to pi. Okay, it comes up often in rules of application in business and science. Okay, and in the case of exponential functions, this is a special exponential function. Again, has a special name. Okay, and the natural base e is called the natural exponential function. Okay, so let's look at an example that involves an equation that has e as its base. So this is a model that we found here that's 6 times e to the 12.77x. Okay, and it says what is the risk of a car accident with a blood alcohol level at 0.08? Okay, R is the risk, X is the blood alcohol concentration level. So for us, we'd want to just plug that into our calculator and type it in just as we see it, 6, and then E to the 12.77 times 0.08. And if we do that correctly, the risk here would be 16.666. Okay. And as you can see, that's what they did on the next slide. And so interpretation here in the context of this problem, okay, it says that rounded in 1 decimal place, the risk of getting in a car accident is approximately 16.7% with your blood alcohol concentration at 0.08. Okay.